So the paper entitled Safety, Energy, and Emissions Impacts of Adaptive Cruise Control and Cooperative Adaptive Cruise Control. I will define them. Probably, maybe some of you don't know what is adaptive cruise control or what is cooperative adaptive cruise control. I will define them clearly here. So I would like to thank my colleagues in this paper, Dr. Ramin Arvin, Dr. Asad Khatak, and Dr. Amir Qiyasi from Latest Inc. He was providing the data for us because I think the data is not public now, but probably in the future they will release the data and they will release it publicly. So let me give you an introduction to this paper. So CAV continues to develop quickly, and we need to understand and study the impacts of CAVs on traffic networks. There are different CAV technologies that potentially can improve transportation safety, mobility, or provide some energy and environment benefits. Adaptive cruise control and cooperative adaptive cruise control are two examples of these technologies that can lead us to substantial improvements in our traffic network. But the question is, how much improvement can ACC and CACC provide for us based on real-world field tests? You know, in previous studies, researchers used simulations to study the impact of these technologies. But recently, due to the field test of US DOTs, we have access to real-world data, and then we can analyze that data and study the impacts. The focus of this study is mainly on ACC and CACC impacts on safety and mobility, energy, and the environment. So what is ACC and what is CACC? Adaptive Cruise Control, or ACC, is an available cruise control system for road vehicles that automatically adjust the vehicle speed to maintain a safe distance from vehicle ahead. You know, I believe most of the new vehicles today, you can add this option to your vehicle, ACC. It has a front radar that can detect the front vehicles or the head vehicle up to 500 feet, or let's say 150 meters. So in ACC mode, your vehicle can only detect one vehicle ahead. And when the radar detects that vehicle, the vehicle can automatically adjust its speed and its spacing to that vehicle, provide a safe situation for you to follow that vehicle. But what is CACC? CACC, or Cooperative Adaptive Cruise Control, is an extension to the ACC concept. Actually, CACC realizes longitudinal automated vehicle control. A CACC system has been developed by adding a wireless V2V communication system and a control logic to the ACC system. What does it mean? If you take a look at the picture in the right corner of the screen, in the top vehicle platooning, you can see each vehicle is detecting the front vehicle. So this is a ACC mode vehicle platooning. So in ACC mode, for example, if the lead vehicle sharply braking, there would be a gap between other vehicles in the platoon to detect that deceleration and react to that. But in CACC, because not only the vehicles can detect the front vehicle with its sensor, they are connected to each other through V2V communication. So if the lead vehicle sharply decelerating, other vehicles immediately can detect that deceleration and react to that. So the reaction time would be so low compared to ACC mode. So what would be the impacts or the consequences of the V2V communication in a platoon? This study wants to quantify the impact of this communication between vehicles in a car platooning. So we use some performance measures to quantify the impacts. For mobility and safety, we use driving volatility or temporal driving volatility. I will define that in a few next slide. Another measure is time to collision. Time to collision is a measure to assess the risk of real-end crashes. For energy, we estimate fuel consumption for the vehicles in different scenarios or modes, ACC, CACC, or manual human-driven mode. And we use Kamal et al. Model to estimate the fuel consumption. And for environmental factor, we calculate the amount of emissions using MOVES mode for EPA. As you can see, the formula here. And then we compare different modes of vehicle platooning to see what is the performance of these technologies. So what is temporal driving volatility? Temporal driving volatility use time series profile of speed as an input and generate a time series profile of volatility. As you can see in this graph, the top one is a time series of speed. The x-axis is time, as you can see, and the y-axis is speed. So, for example, if you take a look at time equal to 200 seconds, you can see a sharp deceleration and then a sharp acceleration. If you look at the driving volatility graph, you can see because of this sharp deceleration and sharp acceleration, you will have high volatility there. So the volatility actually captures the instability of the driving behavior maybe. So if you sharply accelerate or decelerate, the volatility captures that and show that as a unsafe situation. The data that we use were captured by USDOT during some experiments on CAVs named Karma Project or Karma Platform. You can search it on the internet and see what is that. There are 3 phases of Karma Project. Phase 1 started at 2014 and ended in 2016. Karma 2 started since 2000, I believe, 17 to 2018, and right now they are working on Karma 3. So in Karma 1, they developed the platform of CACC and use it in a field experiment, in a field test in Maryland, as you can see in the picture. It's a test track, military test track. 5 automated cars perform a platoon, and they test the CACC and ACC and gather the data. In Karma 2, they use that platform in a highway, and I believe in Karma 3, they will implement it in a larger scale. So I used Karma 1 and Karma 2 database to analyze the performance of CACC and ACC in this paper. The data comprises of 2 different scenarios. In scenario 1, 5 vehicle forms a vehicle platooning in 2 different modes. All vehicles use ACC system or the vehicles use CACC system. As you can see in the top graph here, the top picture here. In scenario 2, the lead vehicle and 3 following vehicles perform the vehicle platooning. The last vehicle is going to join the platoon. So the last vehicle in one mode, manually, by human-driven mode, join that platoon, and in another mode, automatically with CACC platform, the vehicle joins the platoon. So we have these 2 different scenarios. Each scenario has 2 different modes. Remember this. So this is a descriptive statistic of speed in scenario 1 and 2. If you take a look at scenario 1, The number is average of 10 tests in scenario 1. Of course, we have 4 vehicles, 4 following vehicles, and 1 lead vehicle. Just focus on the following vehicles. For example, if you take a look at CACC for the mean value of speed, you can see for all vehicles, the mean value of speed in CACC mode is a little bit higher than ACC mode. What does it mean? It means that probably the average speed using CACC is higher than ACC. And in a larger scale, it will reduce travel time. If you take a look at standard deviation of the speed, you can see for CACC, the standard deviation of speed is much lower than ACC. What does it mean? It means using the CACC or using the communication between vehicles, you're gonna have lower speed variation or speed fluctuation. This means you will have more stable situation, traffic flow in your traffic network. This graph shows the same concept. The left side shows this ACC mode and the right side shows the CACC mode. The top one is speed, time speed graph, and the bottom one is time acceleration graph. If you look at ACC mode, you can see the black line represents the lead vehicle and the colored line represents the following vehicles. So if you see here, we have a deceleration here and the following vehicles using ACC take some time to adjust their speed to the lead vehicle after deceleration. And you can see high speed variation here. But in CACC, you can see the speed variation is much lower. Vehicles can adjust their speed to the lead vehicle after deceleration or acceleration quickly. For acceleration graph, you can see the same things. Vehicles in ACC shows higher acceleration variation compared to CACC mode. There is something else here. If you take a look at the slope of the black line in ACC and CACC in the time speed diagram, the slope shows the acceleration rate. So the slope of the CACC in acceleration is much higher than ACC. What does it mean? It means that the algorithm of the CACC can handle higher acceleration rates than ACC to provide a safe situation. For example, if you use ACC system in your vehicle right now, it's commercially released, the vehicle would not accelerate sharply because it cannot provide a safe situation to accelerate sharply. Probably you will hit the front vehicle. But CACC, due to the connectivity between vehicles, can handle a sharper acceleration. Because, for example, if the lead vehicle sharply accelerates, other vehicles simultaneously understand that the lead vehicle is accelerating and they accelerate at the same time. So due to the connectivity, the algorithm can handle sharper acceleration rate. So in the acceleration time diagram, you can see for during the acceleration period, you can see higher acceleration here in the graph compared to ACC mode. This is scenario 2. In scenario 2, as I discussed, we have a merging vehicle. The red line represents the merging vehicle, starting from speed of 0 here and accelerating and joining the platoon here. So the left side represents the CACC mode, the right side represents the manual mode or human-driven mode. So as you can see, CACC shows less speed variation or acceleration variation. There are two different types of acceleration graph here, longitudinal acceleration and latitudinal acceleration. So CACC provides more smoother speed adjustment of the vehicle in the platoon or the merging vehicle, as you can see here. This is the speed-based driving volatility in scenario 1. So as I discussed, driving volatility captures the instability of the behavior of the vehicle or the driver. So the left side represents the ACC mode, the right side represents the CACC mode. So as you can see in this ACC mode, we have much higher driving volatility during the deceleration. That's why, because the vehicle takes so much time to adjust their speed to the lead vehicle. But during the acceleration, due to the sharper acceleration of the CACC mode, you can see a little bit higher volatility during the acceleration between time 100 to 150. If we aggregate all these values to one number, we can say CACC compared with ACC for following vehicles, we will have near 20% reduction in speed volatility, ranging between 40% to 29% based on the vehicle positioning in the platoon, for example, being the first vehicle or the fourth vehicle. As you can see in the table, the last vehicle shows much reduction in driving volatility in CACC mode. And that's because of the connectivity between vehicles. So there is no difference in CACC being the last vehicle or the first vehicle in the platoon because all vehicles are connected to each other. But in ACC, it does matter because each vehicle should detect the front vehicle. So there would be a gap and the delay to detect it and react to that. That's why the volatility for ACC mode for the last vehicle is much higher than for the first vehicle. You can see in the graph, the red line is much higher than the blue line. But for CACC, it doesn't matter. Mostly they are the same. In scenario 2, the red line represents the merging vehicle. The left side is the manual mode, the right side is the CACC mode. You can see, although the merging vehicle had sharper acceleration, but the speed volatility is a little bit lower than manually driven vehicle. And the platoon, for 4 vehicles in the platoon, you can see much smoother behavior for in CACC mode. If you aggregate the values, we can say CACC compared with manual for following vehicles would have near 60% reduction in volatility, ranging between 54 or 55% to 70% based on the vehicle positioning. Time to collision is another measure for assessing the safety of the vehicles. So what is time to collision? Time to collision is a surrogate safety measure, which is generally defined as the duration of time before 2 objects collide with initial certain conditions. This measure has been widely used to assess the risk of real-end collision. If you take a look at the equation here, the denominator shows the spacing between vehicles in meter or in foot or yard, whatever. And the denominator shows the speed difference. So we said CACC has the ability to adjust the speed of following vehicles with the lead vehicles quicker. So if we have lower speed difference in this equation, we would have higher time to collision. The denominator goes to 0, so time to collision goes to infinite. The results shows that if you take a look at the graph, the descriptive statistics of time to collision values, for the mean value for CACC for all 4 vehicles, you have much higher values compared with ACC mode. This means you have safer situation, or we have safer margins in CACC mode compared to ACC. But the critical value for time to collision is the minimum time to collision. The critical value is near 2 seconds. For example, if your time to collision be below 2 seconds, probably you will have a real-end crash because your reaction time as a human is near 2 seconds, and you don't have enough time to react and decelerate. Here in ACC, the minimum time to collision is near 4 seconds, but in CACC, it's about 8 seconds. We can say about 100% increase in the minimum value or the critical value of time to collision for CACC mode. About fuel consumption, if you take a look at the graph, the purple line represents the CACC mode, at the blue or green line represent the ACC mode. You can see for all 4 vehicles, let's say all 4 forward vehicles or following vehicles, following vehicles shows lower fuel consumption. We can say CACC compared with ACC, we can have a mean reduction about 4%, ranging between 0.5% to 7% based on the vehicle positioning. In scenario 1, where all vehicles only perform a platoon and follow each other. And regarding the emissions, you can see the same mean reduction, about 4%, ranging between 3% to 5% reduction in emission using CACC. The reason is because vehicles have a lower speed variation, lower acceleration variation, and as a result, they will consume less fuel and emit less emissions. What about scenario 2, where we have a merging vehicle? If you take a look at the result, you can see for fuel consumption for the vehicles in the platoon, we have a reduction near 20%. But for the merging vehicle, because it has a higher acceleration rate, the fuel consumption is the same as human-driven mode. It's near about 0.5% increase, but it's not significant. 0.5% is not significant. Regarding the emissions, again, we have about 3% reduction in emission comparing the CACC and manual mode. And for merging vehicle, we have 4% increase due to the sharper acceleration. They constantly accelerate from speed of 0 to 60 miles per hour. So during the constant acceleration, because the acceleration was sharper, it produced more emissions. So we can conclude that CACC as a new technology in CAVs, compared with ACC, we can say ACC is an old-fashioned technology right now. It has been used since 2017 commercially, but CACC, you can't use it right now in real world. But as I said, in Karma project, we are going to implement it in some freeways near Washington, DC. Then if you have an automated vehicle, you can use it. Probably they will implement it for commercial vehicles, trucks, because it's very important for trucks to consume less fuel. So CACC reduced their fuel consumption and probably provide more benefit for them. So CACC compared with ACC reduces the following vehicles' speed-based volatility by 20%. It means lower crash risk. And it increased the minimum time to collision, which means lower real-end crash risk, and reduced the overall fuel consumption of following vehicles by 4%, and reduced the overall emissions of following vehicles by, again, 4%. Thank you. If you have any questions, feel free to ask me.
Thank you so much for Iman. I think I took the same ITS course with you, and then you presented this maybe like a preliminary result back then. So I'm really glad that, because to me, I think this takes a lot of time, in terms of data processing, writing back and forth. So I'm really happy for you that you managed to push it towards the finish line, and this is looking really good. from my
Thank
perspective
you.
now. So yeah, so now we will have some time for our members to ask questions. You can ask, you can ask specifically about the paper, for example, how they deal with the data, or you can ask about just in general, what is the paper submission procedure is like, right? Like how long is the period from the initial submission to the final publication of the paper? So you can ask all sorts of questions. So if you want to ask a question, you can just unmute yourself and start talking. Anyone want to ask a question?
Awesome.
Okay, this is the time that the president asks questions. So okay, so I have a question about the data. So how large is the data, and what is the challenging part of about the data that you have during the process?
The data was not that much large because it was only some experiments. They didn't release the data for all of the tests, but just a sample of that. But the problem in that database is that you need to understand which test is correct or which test is not correct, because their focus in that project was to optimize their algorithm. So I remember there were 89 tests for the Karma project in phase 1 only, in Karma 1, and among 89 tests, only 12 of them were correct. So you need to run some test on the data to see, okay, the data is how many missing value do you have in the data set, or read the description of the data set to see, okay, the data is valid or not, or other things. The challenging part for me was that to contact the Karma project to ask them, okay, which test number is valid or which test number is not valid. For example, there are 4 vehicles in each, there are 5 vehicles in each test. So for example, in one vehicle suddenly disconnected and no data were gathered for that vehicle. So you need to eliminate or delete that test because of that missing value for that vehicle. Cleaning the data, I believe, is the most important part of doing research. If you have a clean data set, you pave the road for writing a paper. When you have a clean data set, you just need to analyze it and it won't take so much time. But cleaning the data is the main part that takes so much of your time to be familiar with the data set and understand what's going on in the data set.
And out of curiosity, what software did you use? What software did you use when you process the data and produce the graphs?
Yeah, I use R to analyze the data and generate the graphs. R Studio actually, but the data gathered in Python, you need to convert it into CSV, then read it with R. So the data format was not CSV, it was something else. You can't open it with R, but you can easily convert it to CSV using Python and then read it with R.
Okay. Another out of curiosity question. From the first initial submission to the journal until it was published, how long is the period?
So August 1st is the deadline for TRB. You can choose to submit it for only presentation or for publication and presentation. if you select publication and presentation, they will consider your paper for both being presented in TRB or being published in TRR journal. After TRB, during, I think TRB is in January, they will let you know that, okay, your paper is going to be published in TRR or not. So probably in December, they will let you know that your paper is rejected for publication or being accepted for publication. My paper was accepted in February, and then after 2 months, responding to the reviewers and editing and handling the proof version, it was published, I believe, 2 weeks ago, I think.
Yeah, so that's about 9 months, right?
9 months, yeah.
9 months, 9 months.
But I would like to say, TRR is a, you know,
Long.
Yeah, it takes so much time to publish something, but it's safe. You know, the rate of accept is high in TRR. So if you just want to submit something for presentation, it's better to choose both publication and presentation. Because when you select only presentation, you will not receive a very good reviews or very good comments. But when you choose publication, they will critique your paper deeply and give you very good comments. So you can improve your paper if you get rejected with the comments, and use the comments and then submit it to another journal.
Yeah, that's one of the beauties of TRB.
Mm-hmm.
Yeah. So do we have other questions from our members? Some members in the survey they talk specifically about, you know, we want to know about data, we want to know about visualization. So this is the opportunity for you to raise that question if you have one. Okay, hearing none. So once again, I would like to thank Iman for spending the time to share about his experience